What if everything we see around us, the stars, the galaxies, the very fabric of space and time, began not with a single explosive moment, but as a shimmering, uncertain ripple in the very nature of reality itself? Picture a moment before moments, a reality so strange and delicate that the laws of physics as we know them hadn't yet decided how to behave. This isn't science fiction. It's one of the most profound ideas at the frontier of cosmology and quantum physics. We're talking about the possibility that the universe itself was born not as a definite, singular event, but as the very first quantum superposition, a cosmic condition where all possibilities existed at once. It's a concept that challenges everything we assume about beginnings. We often imagine the birth of the cosmos as something grand, explosive, and definite, a singular point from which everything emerged. But what if instead the universe flickered into being not as one thing, but as many? What if, in those first fleeting instants, reality was a blur of potential, every possible version of existence overlapping, until something or someone observed it into being? This idea draws us into a world where the rules are both bewildering and beautiful, where the act of observation might not just measure reality but create it. And that's exactly what we're diving into today. In this video, we'll explore 30 captivating theories about the universe's first quantum superposition. From mind-bending hypotheses about parallel realities born from that primordial uncertainty, to the role consciousness may have played in shaping the cosmos, we're about to embark on a journey to the very edges of understanding. This isn't just a story about physics, it's about what it means to exist in a reality that might still be echoing with those first quantum whispers. So settle in, open your mind, and let's explore together how the universe might have begun not with a bang, but with a question. To grasp this radical idea, we must first revisit one of the strangest and most fundamental principles of quantum mechanics. In the tiny world of atoms and particles, things don't behave like the solid, predictable objects we're used to. An electron, for instance, doesn't have a definite location until we measure it. Instead, it exists in a cloud of probability, described by what physicists call a wave function. This mathematical expression encapsulates all the possible places that electron could be, all at once. It's only at the moment of observation, the act of measurement, that this shimmering haze of possibilities collapses into a single, definite reality. We see one specific electron in one specific place. Now, take that bizarre but well-documented quantum quirk and scale it up, apply it to the entirety of everything. That is the heart of our first theory. This theory proposes that before the universe as we know it, there was no singularity, no fiery point of infinite density. There was only a primordial quantum state, a wave function of the cosmos itself. In this initial condition, every possible version of a universe existed in a grand, overlapping superposition. The fundamental constants of nature, the number of spatial dimensions, even the very laws of physics themselves were not yet fixed. They were all potential outcomes, fluctuating in a state of pure potential. One possibility might have had a stronger gravitational force, making stars burn out in milliseconds. Another might have had no weak nuclear force, preventing the formation of the complex atoms necessary for life. In this cosmic probability cloud, they all coexisted, but then something happened, a transition occurred. This is what physicists refer to as the cosmic wave function collapse. The question of what triggered this monumental collapse is one of the deepest mysteries. Some interpretations suggest it was a natural, inevitable process called decoherence. In the subatomic world, decoherence is what happens when a quantum system interacts with its environment. Those interactions effectively measure the system, causing it to lose its quantum properties and settle into a classical, definite state. On a universal scale, perhaps the incredibly dense and energetic conditions of the early cosmos caused its own wave function to decohere almost instantly, freezing one specific set of physics into place. Other, even more mind-bending interpretations, like the participatory anthropic principle, suggest that observation itself was the key, that the universe required a conscious observer to bring it into being. This doesn't necessarily mean a human looking through a telescope at the Big Bang, but rather that the act of measurement is a fundamental part of reality. In this view, the first sentient beings to eventually evolve and look out at the cosmos completed a cosmic loop, their observation retroactively solidifying the universe's ancient quantum passed into the history we now study. This theory suggests that the specific physical constants we measure aren't arbitrary. They are the only ones that could have produced observers capable of measuring them in the first place. The implications of this initial collapse are staggering. It means the precise tuning of our universe, the exact strength of gravity, the mass of an electron, the value of the cosmological constant wasn't preordained. It was selected almost at random from an infinite menu of possibilities during that first great quantum transition. The reality we inhabit is just one roll of the dice, one possible outcome that somehow won the cosmic lottery. This provides a powerful, if speculative, answer to the question of why our universe seems so perfectly fine-tuned for life. It's not that the universe was designed for us. It's that we emerged in a universe that happened to have the right conditions, selected from a vast multiverse of possibilities at the moment of that first and most important collapse. But if the first theory leaves us marveling at a single, lucky roll of the cosmic dice, the second theory presents an even more expansive vision, one where every single possibility becomes reality. This is the idea of the multiverse genesis. Imagine that initial quantum superposition of the cosmos never actually collapsed at all. Instead of solidifying into one universe, that primordial haze of potential began to inflate, to stretch and expand at a rate beyond comprehension, and in doing so, it didn't choose one path, it chose all of them. Each and every possible outcome contained within that first quantum fluctuation was simply carried along for the ride, each one inflating into its own separate, full-fledged universe, complete with its own unique set of physical laws and constants. The moment of creation wasn't a decision, it was a divine sorting hat, placing every potential reality into its own cosmic pocket. This process is often described through the lens of eternal inflation. Think of the fabric of space-time as a vast, bubbling pot of water just beginning to boil. Each bubble that forms and rises to the surface isn't just a pocket of air. It's an entire universe nucleating out of the seething, high-energy quantum foam of the multiverse. Our entire observable cosmos, with its hundreds of billions of galaxies, is just one single bubble in this infinite cosmic froth. And the driving force behind this incredible expansion is believed to be a peculiar state of energy called the inflaton field. In the earliest instance, this field was caught in a false vacuum state, a condition of incredibly high energy that exerted a repulsive gravity, causing space to expand exponentially fast. But like a ball perched precariously on a hill, this state was unstable. Quantum fluctuations would eventually cause the field to roll down its energy landscape to a more stable, lower energy state, a transition that released the energy to form all the matter and radiation in our universe. But here's the twist. According to eternal inflation, while our local patch of the universe underwent this transition and stopped inflating, the overall inflaton field never completely settled down. The expansion of the multiverse at large becomes, well, eternal. New universe bubbles are continuously popping into existence, each one a separate branch stemming from that original, all-encompassing superposition. Within this framework, those quantum fluctuations aren't just minor details, they are the architects of reality. A tiny random jitter in the inflattened field in one region could mean that region inflates a little slower, resulting in a universe with a slightly stronger gravitational constant. A fluctuation in another region might tweak the strength of the nuclear forces, creating a reality where atoms cannot even form. Every conceivable permutation of physical law, every possible value for every fundamental constant, is realized in some bubble universe out there. In one universe, stars might never ignite. In another, gravity could be so weak that matter never clumps together into planets. And in a stunningly rare subset of those universes, like our own, the numbers just happen to line up perfectly to allow for galaxies, stars, planets, and life. This offers a powerful, if humbling, solution to the fine-tuning problem. Our universe isn't fine-tuned, it's simply an inevitability. With an infinite number of universes, every possible outcome, no matter how improbable, must occur somewhere. We don't find ourselves in a universe fine-tuned for life because it was designed for us. We find ourselves in such a universe because we couldn't possibly find ourselves anywhere else. Visualizing this is a challenge for the human mind, but one way to picture it is as an ever-growing fractal-like tree. The trunk is that first quantum superposition. As inflation takes hold, the trunk branches infinitely, with each branch representing a new universe bubbling into existence with its own unique properties. From each of those branches, new branches sprout, and so on forever. We are on one single leaf of this unimaginably vast tree, utterly unaware of the other leaves except through the profound implications of the theory itself. This is the multiverse genesis, a theory that transforms the moment of creation from a singular event into an ongoing, eternal process of becoming, where the first quantum whisper of the cosmos never truly faded away, it simply echoed into infinity. Building on the idea of a multiverse born from inflation, we venture into an even more fundamental realm, the very first moments where time and space as concepts were struggling to exist. This brings us to our third theory, which dives into the heart of the singularity problem and proposes that quantum gravity held the universe in its first and most profound superposition. To understand this, we have to confront the greatest incompatibility in all of physics. Our two most successful theories, quantum mechanics, which rules the very small, and general relativity, which describes gravity and the cosmos, utterly break down when forced to confront each other. Their clash becomes most violent at the very beginning of everything, at a point we call the Planck epoch. This was the first 10 to the minus 43 seconds of the universe. A timescale so short it's almost meaningless to us. At this moment, the entire cosmos was compressed into a volume smaller than a single atom, yet it contained all the energy and mass that would eventually become every galaxy and star. According to classical general relativity, this point is a singularity, a place of infinite density and curvature where the laws of physics simply cease to function. It's a mathematical error sign in our equations, a glaring signal that our theory is incomplete. We know it's wrong, but we didn't know how. This is where quantum gravity theories like loop quantum gravity and string theory step in to rewrite the cosmic origin story. They suggest that the singularity never actually happened because at that scale, space-time itself becomes fuzzy and uncertain. Think of it this way. In our everyday world, we think of space as a smooth, continuous stage upon which particles move. But what if that stage is an illusion? What if, when you zoom in past atoms, past electrons, down to the Planck scale, the stage reveals itself to be made of a fabric that is granular, discrete, built from tiny, indivisible threads or loops? This is the core proposal of quantum gravity, that space-time is not a smooth continuum but is quantized, made of minuscule, vibrating units of space and time. In the Planck epoch, the energy was so unimaginably high that these fundamental building blocks of reality were violently fluctuating. There was no smooth stage, there was a bubbling, frothing quantum foam. In this foamy, probabilistic sea, the geometry of spacetime wasn't fixed. It existed in a superposition of all possible configurations. One moment, space might be tightly curled into 11 dimensions. The next, it might be stretched into 4. The very concepts of before and after lose their meaning because time itself was just another fluctuating variable in this quantum mix. This is the universe's first quantum superposition, not just of matter or energy, but of the very arena in which physics plays out. Visualize it as a stormy ocean where the waves aren't made of water, but of potential geometries, each crest and trough representing a different possible shape for spacetime, all existing simultaneously. Loop quantum gravity offers a particularly elegant resolution to the singularity problem. It proposes that the gravitational field is woven from networks of these tiny loops. As we rewind time towards the Big Bang, the density doesn't spiral off to infinity. Instead, the loops reach a maximum point of compression and then they bounce. The universe didn't emerge from a singularity, it rebounded from a previous state of collapse. Our Big Bang was not a beginning from nothing, but a great bounce from a previous cosmic phase. And in that moment of the bounce, as one universe was collapsing and another was expanding, the geometry of spacetime would have been in its most profound superposition, a quantum bridge between two cosmic epochs. String theory approaches this from a different angle, suggesting that the fundamental objects in the universe are not point-like particles but tiny, vibrating strings. Their different vibrational modes give rise to all the particles and forces we see. In the early universe, these strings would have been excited to incredibly high energies, and their interactions would have literally shaped the dimensions of space. Some theories within string theory suggest our universe is a three-dimensional membrane, or brane, floating in a higher dimensional bulk. A collision between two such branes could have ignited our Big Bang, with the immense energy of the collision seeding the hot, dense universe we know. In this view, the quantum superposition wasn't just of our universe's geometry, but of all the possible ways these higher dimensional objects could interact and create new worlds. This perspective fundamentally changes our questions. Instead of asking, what came before the singularity, we can ask, what was the universe doing in its quantum gravitational phase? The answer appears to be that it was exploring every possible option. It was a reality in a state of becoming, not being. This resolves the singularity not by finding a smaller point, but by eliminating the point entirely and replacing it with a probability cloud, a wave function of the universe that describes a superposition of all possible initial geometries. It suggests that the definite classical universe we observe today froze out from this quantum frenzy as it expanded and cooled, its waves of possibility gradually decohering into the single, solid spacetime we now call home. This leads us to a theory so provocative it blurs the line between physics and philosophy, suggesting that the very existence of the cosmos might be intertwined with the emergence of consciousness itself. This is the observer-driven cosmos hypothesis, an idea that pushes the quantum strangeness of the beginning to its ultimate and perhaps most unsettling conclusion. If the infant universe was truly in a superposition, a question naturally arises: what was the observer? What or who finally looked at the cosmos and caused its wave function to collapse into the definite reality we now inhabit? Some interpretations of quantum mechanics, particularly the one put forth by physicists John von Neumann and Eugene Wigner, take the role of observation to its logical extreme. In their view, the measurement problem isn't solved by the environment or complex instruments. They argue that all physical processes, including the operation of a measuring device, are themselves governed by the deterministic laws of quantum mechanics and are therefore part of a larger, evolving wave function. The only thing that can truly collapse a quantum state, they propose, is the irreducibly non-physical act of conscious awareness. In the lab, this means it's not the photon detector that collapses a photon's wave function. It's the moment a conscious mind becomes aware of the detector's reading. Now scale this idea up to the cosmic level. Apply it to that first, magnificent superposition of all possible universes. The theory suggests that this primordial quantum state could not have collapsed on its own. It required an observer, but who could have been present to witness the birth of everything? This is where the idea becomes truly mind-bending, venturing into the realm of the participatory anthropic principle. It proposes that the first conscious observers were not present at the beginning, but rather their eventual emergence billions of years later was what made the beginning possible. In a dizzying causal loop, the first sentient beings to evolve and look up at the stars, to observe the cosmos and its laws, retroactively collapsed the universe's wave function at the moment of its creation. Their act of observation reached back through time to select one history out of the countless possibilities, solidifying the Big Bang into the specific event that would eventually lead to them. Think of it as a cosmic version of the famous double-slit experiment, where a particle seems to decide whether to behave as a wave or a particle based on whether we are watching. Now imagine the entire universe is the particle, and the slit is the moment of creation. Without an observer, the universe's history remains a blurry, unrealized potential of all possible paths. But the moment a conscious entity comes into existence and looks back at that origin point, it forces the entire timeline to snap into focus, choosing one specific and consistent history. We aren't just living in a universe that allowed for life. Our conscious observation is the very reason this particular universe exists at all. The fine-tuning isn't a lucky accident. It's a prerequisite for the observers who would one day complete the circuit of reality. The philosophical implications of this are staggering. It places consciousness not as a passive byproduct of the universe, but as an active participant in its very foundation. It suggests a universe that only becomes fully real when it is perceived, a cosmic story that requires a reader to give it meaning. Critics, however, point out the monumental problems with this view. The most glaring issue is the problem of infinite regression. If a conscious observer is needed to collapse a quantum state, then what collapsed the wave function of the particles that eventually formed the first observer's brain? It seems to create an unbreakable loop where life requires a definite universe to exist, but a definite universe requires life to exist. Some proponents try to sidestep this by suggesting a universal consciousness or proto-consciousness inherent in the laws of physics, but this often moves the discussion from testable science into the realm of metaphysics. Despite the controversies, the idea forces us to confront the deepest questions about the relationship between our minds and the reality we perceive. It challenges the classical, objective view of a universe that exists independently of us, suggesting instead a cosmos that is deeply relational. Whether one finds it inspiring or implausible, the observer-driven cosmos theory remains a powerful reminder that in the quantum realm, the line between the observer and the observed is perhaps the most fundamental mystery of all. While the idea of an observer-driven cosmos is deeply philosophical, our fifth theory grounds the universe's first superposition in something far more concrete, yet equally astonishing: information. This is the holographic principle, a concept that suggests our magnificent three-dimensional universe, with its galaxies, stars, and planets, might be a grand projection, a cosmic hologram emerging from a two-dimensional surface encoded with quantum information. To grasp how this relates to the first superposition, we need to journey to the edge of a black hole. The story begins with a profound discovery about black holes. Physicist Jacob Bekenstein found that a black hole's entropy, which is a measure of its information content, its disorder, is not proportional to its volume as one might expect. Instead, it is proportional to the surface area of its event horizon. This was bizarre. It implied that all the information describing everything that ever fell into a black hole is not lost within its vast interior, but is somehow smeared and stored on its two-dimensional boundary. Stephen Hawking later showed that black holes evaporate, raising the terrifying information paradox. If a black hole vanishes, does the information it swallowed disappear forever, violating a fundamental law of quantum mechanics? The holographic principle emerged as a radical solution, proposing that information is never lost because it was never truly in the three-dimensional volume to begin with. The three dimensions are an illusion. The true reality is the two-dimensional information painted on the surface. Now take this concept and apply it to the entire cosmos. Our universe has a horizon, the cosmological horizon beyond which light has not had time to reach us since the Big Bang. The holographic principle boldly suggests that our entire observable universe can be described by a theory that lives on this distant boundary. All the particles, forces, and the very fabric of space-time that we experience in three dimensions are like the rich, moving image on a movie screen. The real action, the fundamental code, is contained in the two-dimensional pixels of that screen. This is formally realized in the add-s/CFT correspondence, a powerful concept in string theory that provides a mathematical dictionary. It shows a perfect equivalence between a theory of gravity operating in a hypothetical anti-de Sitter space, a type of universe with negative curvature, and a conformal field theory, which is a quantum theory without gravity that operates on that universe's boundary. So, what does this have to do with the universe's first quantum superposition? Imagine the primordial state of everything. Before the Big Bang, before any of the dimensions we know had stabilized, there was this foundational two-dimensional surface. This surface wasn't made of matter or energy in the traditional sense. It was made of quantum information, bits or qubits fluctuating in a state of pure potential. Each possible configuration of these information bits represented a different possible universe. One pattern might correspond to a universe with 4 forces. Another pattern might describe a universe with 10 spatial dimensions. In this initial state, all these patterns existed simultaneously. The information on the boundary was in a massive, cosmic-scale quantum superposition. The birth of our universe, then, was not an explosion in space, but a projection from this informational surface. This process is often called the decoding of the cosmic hologram. As this two-dimensional information stabilized, perhaps through a process akin to quantum decoherence, it began to project the holographic illusion of a three-dimensional world. The fuzzy probabilities of the quantum information patterns on the boundary crystallized into the definite laws and constants we measure today. The superposition didn't collapse within space. The collapse of the superposition on the boundary created space itself. Visualize it as a vast, shimmering sheet of light covered in ever-shifting, intricate patterns. Suddenly, one pattern resolves, becoming stable and coherent, and from it, an entire universe blossoms into being, its depth and complexity an emergent property of that two-dimensional data. This provides a breathtakingly elegant framework for understanding the first quantum state. It suggests that the most fundamental building blocks of reality are not tiny strings or loops, but bits of information. The universe began as a quantum computation, and the output of that computation is everything we see and feel. The holographic principle doesn't just tell us how the universe might have gotten started, it redefines what the universe fundamentally is. It's a reality where information is the true currency of existence, and our perception of a three-dimensional world is the most beautiful and complex projection ever imagined. But if the holographic principle redefines the very dimensions of reality, our next theory challenges something even more fundamental to our experience, the flow of time itself. This is the idea of the timeless wave function, a perspective that suggests the universe's first quantum superposition wasn't a momentary event in the distant past, but is in fact an eternal, unchanging state that exists outside of time altogether. To grasp this, we need to venture into the world of quantum cosmology and a deceptively simple-looking equation that attempts to describe the entire cosmos in one breath. This equation is called the Wheeler-DeWitt equation, named after physicists John Wheeler and Bryce DeWitt. It was one of the first serious attempts to apply the rules of quantum mechanics to the whole universe to find a wave function of the cosmos. But this equation contains a feature so startling that it reportedly disturbed its own creators. The problem is that the time variable, the familiar t that ticks away in every other physics equation, completely disappears. It simply isn't there. The Wheeler-DeWitt equation describes a static universe. It doesn't tell you how the universe evolves in time. It suggests that the universe, in its most complete description, is frozen. It just is. This presents us with a profound paradox. Our lived experience is one of relentless change, of past, present, and future. How can this dynamic flow emerge from a fundamental reality that is timeless? Proponents of this view argue that time is not a fundamental ingredient of the universe, but an emergent property, much like temperature emerges from the frantic motion of atoms. We don't find little atoms of temperature, we find moving particles, and their average kinetic energy is what we perceive as heat. In the same way, the theory suggests that what we experience as the flow of time emerges from the relationships between events within the universe. The universal wave function described by the Wheeler-DeWitt equation isn't evolving. It encompasses all possible configurations of the universe at once in a single, vast, timeless superposition. Visualize this not as a movie, but as a single, intricate sculpture. A movie has a timeline. It has a beginning, a middle, and an end that unfolds sequentially. This timeless view suggests the universe is more like a breathtakingly complex statue. Every moment from the first quantum fluctuation to the formation of the last star exists simultaneously, carved into the fabric of this static quantum landscape. Our conscious journey from birth to death is not a trip through time, but a path we trace across this eternal structure. The first superposition wasn't first at all. It is a permanent feature of this landscape, forever entwined with every other possible state. This has stunning implications for the very idea of a beginning. If the fundamental description of reality is timeless, then asking, what happened before the Big Bang? Becomes a bit like asking, what is north of the North Pole? It might be a question that stems from a misunderstanding of the framework. In this view, the Big Bang is not a temporal beginning but a particular feature within the timeless wave function, a point where the geometry of the universe takes on a specific form. The wave function itself has no beginning and no end. It simply defines the probability for any particular universe to exist within its grand, static probability distribution. The challenge, of course, is reconciling this with our undeniable experience of a flowing, dynamic present. How does change arise from something changeless? The emerging answer often involves the concept of a clock within the universe. Since there is no external time, something inside the system must serve as a reference for change. Imagine the universe is described by two variables, the size of the universe and the strength of a material field within it. The Wheeler-DeWitt equation gives a fixed relationship between these two. As one changes, the other must change in a corresponding way. We can then choose to call one of these variables our clock. For instance, we could say that the size of the universe is our clock. Its expansion isn't happening in time. The expansion itself defines time. Each increment of size corresponds to a tick, and against this internal clock, everything else appears to evolve. This is how a timeless reality gives rise to the compelling illusion of a flowing time, where the eternal superposition of the wave function is perceived by us from the inside as a cosmic history unfolding. Yet if the timeless wave function asks us to abandon our intuition about time, our seventh theory brings us back to a moment, not of static being, but of spontaneous creation from the utter void. This is the idea of quantum fluctuation genesis, a concept that suggests our entire universe could be the ultimate free lunch, a random, temporary burst of energy that somehow became permanent, emerging from a pre-existing, featureless vacuum. To understand how something can come from nothing, we must first redefine what we mean by nothing, and to do that, we turn to one of quantum mechanics' most fundamental rules. This rule is Heisenberg's uncertainty principle. It states that on the subatomic scale, there is a fundamental limit to how precisely we can know certain pairs of properties. For instance, the more precisely you know a particle's energy, the less precisely you can know how long it possessed that energy. This isn't a limitation of our measuring devices, it's a built-in feature of reality. This inherent fuzziness has a startling consequence. It means that empty space can never be truly, completely empty. If we could examine the vacuum at the smallest possible scale, we wouldn't find a dead, static void. Instead, we would find a seething, bubbling cauldron of activity now called the quantum foam. Pairs of particles and their antiparticles, so-called virtual particles, are constantly flickering into and out of existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and paying the energy back. These are not mathematical tricks. Their effects are real and measurable, such as the Casimir effect, where two metal plates placed extremely close together in a vacuum experience a slight push from these virtual particles popping into being on the outside. Now take this well-established quantum quirk and scale it up to a literally cosmic degree. The theory of quantum fluctuation genesis proposes that our universe began as one such fluctuation, but on an unimaginable scale. In the beginning, there was a primordial void, a state of true nothingness with no space, no time, no matter. But due to the uncertainty principle, this nothingness was inherently unstable. A tremendous quantum fluctuation occurred, borrowing energy to spontaneously generate a seed of spacetime itself. In that first fleeting instant, this newborn universe was a tiny bubble of energy, a virtual universe that should have almost immediately vanished back into the void from whence it came, its energy debt due. But something extraordinary happened. Theoretical models suggest that the specific conditions within this fluctuation, potentially driven by a peculiar state of energy called a false vacuum, caused this bubble to undergo a period of hyper-fast expansion known as inflation. This rapid stretching of spacetime happened so quickly that the tiny universe ballooned to an enormous size in a fraction of a second. Critically, this expansion effectively locked in the energy, preventing the universe from having to repay its debt. The virtual particle had become real, the temporary loan became a permanent grant, and our cosmos was born. This initial state would have been the ultimate quantum superposition. Before inflation locked everything into place, this nascent universe fluctuation wasn't a single, definite entity. It was a probability cloud, a potential reality hovering between existence and oblivion. It represented a superposition of all possible initial conditions, different possible geometries, different fundamental constants, different laws of physics. It was a cosmic question mark. The process of inflation then acted as the great decoherer, its rapid expansion forcing this quantum possibility to choose a single classical path, freezing one specific set of rules into the fabric of reality as we know it. Visualize this as the ultimate close-up shot. We see a dark, featureless void, but then we zoom in closer and closer until the empty space resolves into a frenzied, frothing sea of virtual particles sparkling in and out of existence. One of these tiny sparks, through a random statistical chance, doesn't fizzle out. It swells, glowing brighter and brighter, rapidly inflating into a magnificent, shimmering bubble of space-time that continues to expand, becoming the entire observable universe. This theory doesn't require a creator or a prior state. It requires only the bizarre but undeniable rules of quantum physics, suggesting that in the grand scheme of things, universes might be as natural and common as particles. Supersymmetry offers a breathtakingly elegant vision for the universe's first quantum state, one built not on chaos but on a profound and beautiful symmetry. This theory, often nicknamed SUSY, proposes that in the earliest moments of the cosmos, the fundamental forces and particles we know today were not separate entities at all. They were unified, part of a single, symmetrical whole where every particle of matter had an identical, yet unseen, partner particle of force, and vice versa. This framework suggests the first quantum superposition was not just a blur of possibilities, but a perfectly balanced dance between partners that had not yet chosen their roles. To understand this, we need to meet the characters in this cosmic drama. The universe is built from two main families, fermions and bosons. Fermions, like electrons and quarks, are the stubborn individualists. They are the building blocks of matter, and they hate to be in the same state as each other, which is why solid objects exist and you don't fall through your chair. Bosons, like photons and gluons, are the social force carriers. They love to congregate in the same state, and they mediate the forces that allow fermions to interact. Supersymmetry proposes a deep and fundamental link between these two families. It states that for every known fermion, there should be a bosonic superpartner, and for every known boson, a fermionic one. The electron, a fermion, would be paired with a selectron, a boson. The photon, a boson, would be paired with a photino, a fermion. In this symmetric state, matter and force are two sides of the same coin. In the extreme energy and density of the universe's first quantum superposition, this symmetry would have been unbroken. All these particles and their superpartners would have existed in a magnificent, undifferentiated haze. They wouldn't have had distinct masses or properties. They were all effectively equivalent, existing in a quantum state where their identities were blurred together. This wasn't just a superposition of locations or energies, but a superposition of the very categories of existence. The universe was in a state of pure potential, waiting to decide which particles would become matter and which would become force carriers. Visualize this as a perfectly pristine, symmetrical snowflake, each arm identical to the next, representing the perfect balance between fermions and bosons. But this perfect state was fragile. As the universe expanded and cooled in the first fleeting instants after the Big Bang, its energy dropped. This is where a process called spontaneous symmetry breaking occurred. Much like water freezing into ice, where the perfectly symmetric liquid state gives way to a crystalline structure with a preferred orientation, the unified supersymmetric state had to choose. It could no longer sustain that perfect balance. The symmetry broke and the superpartners diverged. The theory suggests that most of these superpartners acquired incredibly high masses, becoming so heavy that they decayed almost instantly into the lighter, stable particles we detect today. This is why we don't see selectrons or photinos zooming around everywhere. They collapsed out of the primordial quantum superposition, leaving behind the asymmetric, diverse universe of distinct particles and forces we now inhabit. This breaking of supersymmetry would have been the ultimate cosmic phase transition, and it would have left its mark. The energy released as the symmetry broke could have been the very driver of the inflation that stretched the universe to such an enormous size. Furthermore, the lightest of these superpartner particles, often called the lightest supersymmetric particle or LSB, is a prime candidate for the mysterious dark matter that makes up most of the mass in the universe. If this is true, then the evidence for supersymmetry isn't just hidden in our particle accelerators. It's all around us, woven into the very fabric of every galaxy. The hunt for this evidence is one of the great quests of modern physics. For decades, scientists at facilities like the Large Hadron Collider have been smashing protons together at unprecedented energies, hoping to create these super-heavy superpartners fleetingly in the lab, recreating a minuscule echo of that primordial symmetric state. While no definitive discovery has been made yet, the mathematical beauty and explanatory power of supersymmetry keep it at the forefront of theoretical physics. It represents a compelling vision of the beginning, a moment of perfect quantum order and balance, whose graceful breakdown gifted us the rich, complex, and life-giving universe we call home. While supersymmetry paints a picture of a beginning grounded in elegant mathematical order, our ninth theory ventures into the opposite extreme, proposing a cosmos born from the most profound and chaotic randomness imaginable. This is the idea of the quantum Boltzmann brain, a hypothesis so strange it suggests the first observer to collapse the universe's wave function might not have been a future civilization, but a fleeting, self-aware structure conjured randomly from the quantum foam itself. To even approach this concept, we must first travel back to the 19th century and a physicist named Ludwig Boltzmann, who grappled with a deep paradox about order and disorder. Boltzmann helped found the field of statistical mechanics, which explains how the behavior of countless atoms gives rise to the laws of thermodynamics. One of its core principles is that entropy or disorder always increases. It's why a drop of ink spreads evenly through a glass of water but never spontaneously reforms into a drop. The universe is on a one-way trip from order to disorder, but Boltzmann realized that in a truly infinite and eternal universe, even the most improbable events must eventually happen. Given enough time, the random jostling of atoms could, by sheer accident, arrange themselves into any configuration, no matter how complex. A hurricane could blow through a junkyard and randomly assemble a perfectly functioning jet engine. Or, more pertinently, a random fluctuation in the void could spontaneously assemble a fully formed, conscious human brain, complete with a lifetime of false memories that exists for just a moment before dissolving back into chaos. This hypothetical entity is what we now call a Boltzmann brain. Now, inject this bizarre thought experiment into the quantum realm of the very first moment. The quantum Boltzmann brain theory proposes that in the universe's initial, seething quantum superposition, that primordial state of infinite potential, the fluctuations weren't just about energy or geometry. They were also fluctuations in information and organization. Among the countless possibilities flickering in that probabilistic haze, there was a non-zero chance of a fluctuation so precise and complex that it formed a self-aware observer. This wouldn't be a brain made of biological neurons as we know it, but a coherent structure of energy or information, momentarily stable enough to possess a conscious experience. And according to the more radical interpretations of quantum mechanics, that momentary act of consciousness, its observation of itself and its environment, would have been enough to collapse the wave function of the entire universe around it. Think of it as the ultimate example of the tail wagging the dog. Instead of a universe evolving over billions of years to produce observers, a random observer spontaneously forms in the first instant, and by the very act of perceiving, defines the universe that will contain it. This brain would not emerge into a pre-existing world. Its observation would literally create that world, retroactively establishing a consistent history that would explain its own existence. It would have a memory of a past that never actually happened, in a universe that had no past until the brain observed one into being. The implications tie directly into the anthropic principle. We believe we live in an old, vast universe fine-tuned for life because that is the only kind of universe that could produce real, evolved observers like us. But if Boltzmann brains are possible, then it is astronomically more likely for a single brain to fluctuate into existence with false memories of such a universe than for the entire, incredibly ordered universe to actually evolve. We should, statistically, be Boltzmann brains ourselves, momentarily hallucinating a grand cosmos from a featureless void. This, of course, leads to a profound and unsettling paradox. The theory seems to predict that disembodied brains with illusory memories should be the most common form of conscious experience in the multiverse, making it deeply suspicious that we find ourselves in a stable, ordered universe that has existed for billions of years. Most physicists consider this reductio ad absurdum a logical argument that demonstrates the theory is likely flawed. The fact that we are having a coherent, continuous experience is the strongest evidence against the idea that we are such fleeting fluctuations. Yet, the idea persists as a fascinating limit case, a reminder of the strange bridges that can be built between quantum mechanics, cosmology, and the nature of consciousness itself. It represents the absolute extreme of a universe whose beginning was not just a quantum event, but a deeply personal and inexplicably random one. But to truly grasp the scale of this choice, we must venture into the hidden, curled-up dimensions that string theory proposes. While we experience 3 dimensions of space and 1 of time, string theory requires more often 10 or 11 dimensions in total for its equations to work. The theory suggests that these extra dimensions are not vast and expansive like our own, but are fantastically small, curled up into intricate, complex shapes at every single point in space. The specific geometry of these hidden shapes is absolutely critical. It acts like the wiring diagram of reality, determining how strings vibrate, interact, and ultimately, what laws of physics emerge in the large, observable universe. A slight alteration in this microscopic geometry could change the mass of an electron, the strength of gravity, or even the number of fundamental forces. The mathematical term for these possible shapes is a Calabi-Yau manifold, a beautifully complex and multi-dimensional object that looks different from every angle. Now apply this to the universe's first quantum state. The theory suggests that in the beginning, these extra dimensions were not fixed. They were not one specific Calabi-Yau shape, but a quantum superposition of all possible Calabi-Yau shapes. The universe hadn't yet chosen its wiring diagram. It was a blur of every conceivable configuration, each one representing a different set of physical laws and constants waiting to be born. This is the famous string theory landscape, not a physical place, but a cosmic-scale probability space containing a staggering 10 to the 500 possible stable configurations, each one a potential universe with its own unique physics. Our cosmos was not a single point, but a probability wave washing over this vast landscape of potentialities. The moment of creation, then, was not an explosion, but a kind of cosmic annealing. As the universe expanded and cooled from its initial hot, dense state, this quantum superposition of geometries began to decohere. The wave function collapsed, and one specific Calabi-Yau manifold was selected from the near-infinite array of possibilities. The strings that make up everything suddenly found themselves in a stable, defined environment, and their allowed vibrational modes crystallized into the specific particles and forces we now know: quarks, electrons, photons, and the rest. The dice were thrown, and our particular set of physical laws was the result. Visualize this as a magnificent, hyper-dimensional kaleidoscope, its patterns shifting and flowing through an endless dance of forms. Then, suddenly, the turning stops. One intricate, snowflake-like pattern snaps into focus, frozen in place, and from that precise and beautiful geometry, our entire universe unfolds. This provides a breathtakingly elegant, if complex, framework for the fine-tuning problem. We don't live in a universe that is inexplicably perfect for life. We simply live in one that successfully navigated the string theory landscape to a stable point that allows for complex structures. In a multiverse of unimaginable diversity, with every possible set of laws realized somewhere, our existence in this particular universe becomes a statistical inevitability rather than a miracle. The profound challenge, of course, lies in moving this beautiful mathematics into the realm of testable science. How do we probe these incredibly small, curled-up dimensions? Some hope that faint echoes of this initial geometric choice might be imprinted on the cosmic microwave background radiation, the afterglow of the Big Bang. Others look for signatures in the behavior of the most energetic cosmic rays or for subtle effects in particle colliders. For now, the string landscape remains a compelling and majestic map of possibility, a theory that suggests the first quantum superposition was a choice between an infinity of worlds, and we are the heirs to one specific and very fortunate geometry. Now, if the string landscape presents us with a cosmos where geometry is destiny, our 11th theory offers a radically different perspective, one that strips away the continuous fabric of spacetime itself and proposes that the universe's first quantum state was a matter of pure potential connections. This is the causal set theory, an approach that suggests reality is not smooth and flowing, but is instead built from a vast number of discrete, fundamental grains of spacetime. In this view, the first superposition wasn't over energies or geometries, but over something more fundamental, the very relationships between events. The core idea is both simple and profound. The theory posits that the fundamental building blocks of the universe are not particles or strings, but simple, dimensionless points. But a random collection of points isn't a universe, it needs structure. That structure comes from the causal relations between them. Each point represents a single event, the most basic possible happening. The theory says that what truly defines reality is which events can influence which other events. Point A can causally affect point B if a signal or particle could travel from A to B without exceeding the speed of light. This web of before and after relationships is what weaves the points together into the ordered fabric of spacetime we experience. The stunning revelation is that if you know the complete set of points and all the causal connections between them, you can reconstruct the entire geometry of spacetime, its curvature, its dimensions, even the flow of time itself. Spacetime is not the stage, it is a secondary phenomenon that emerges from this underlying network of causal links. Apply this to the universe's very first moment. There was no pre-existing arena of time and space. Instead, there was a quantum cloud of these fundamental points, a kind of cosmic dust. But in this initial state, the causal relations between these points were not fixed. They existed in a massive, all-encompassing superposition. For any 2 points, the connection, the answer to the question, "Can you influence me?" was not a definite yes or no. It was a probability. The entire nascent universe was a blur of maybe, a haze of potential cause and effect relationships waiting to be resolved. This probabilistic network elegantly avoids the singularity problem that plagues classical relativity. There is no point of infinite density because reality is fundamentally discrete and granular from the outset. The universe didn't emerge from a singularity, it emerged from this quantum cloud of could be. Visualizing this is a challenge, but imagine a vast, dark canvas. Suddenly, a few specks of light appear, but they are not connected. Then, more and more points flicker into existence, but they are all shimmering, their connections to one another fluctuating. A line of potential causality might flash between 2 points, only to vanish and be replaced by another. It's a pointillistic storm of potentiality. Then, gradually, through a process like quantum decoherence, these probabilistic connections begin to stabilize. Specific causal pathways are chosen, locking into place. As more points are added and more connections are fixed, an ordered structure emerges from the chaos. This network of solidified causal links is what we now perceive as the irreversible flow of time and the vast, expanding geometry of space. The first quantum superposition was this state of pure relational potential, and its collapse gave us the arrow of time and the reliable universe we call home. This perspective brings us to a theory that places consciousness itself at the very heart of cosmic creation, an idea that transforms the universe from a cold, mechanical system into a deeply participatory reality. This is John Wheeler's participatory anthropic principle, a concept that suggests observers are not just passive inhabitants of the cosmos, but active participants required to bring it into being. Wheeler, a towering figure in physics who helped shape our understanding of black holes and quantum theory, took the observer effect and scaled it to its ultimate conclusion. If, in the lab, the act of observation collapses a particle's wave function, then on a cosmic scale? Could the act of observation by sentient beings be what collapsed the universe's own wave function, selecting our specific reality from the initial superposition of all possibilities? In this view, the universe's first quantum state wasn't just a fog of potential energies or geometries. It was a superposition of every possible observer-dependent reality. One branch of this probability cloud might have contained a universe that evolved dinosaurs as the dominant intelligent species, who then looked up at the stars and wondered about their origin. Another branch might have contained a reality where silicon-based crystals developed consciousness. Our own branch is the one where carbon-based life forms on a small rocky planet eventually evolved to gaze back at the cosmos. The profound, almost circular logic of the principle is that these observers are necessary to give the universe its definite form. The universe had to have the potential for life in order for life to eventually emerge and, in the act of observing, retroactively solidify that specific potential into the actual history we now study. It's a closed loop of creation where the universe and the observer bring each other into existence. This idea is often illustrated with Wheeler's own metaphor of the 20th century quantum game show. Imagine a panel of lights labeled with the names of various particles: electron, photon, quark. In the beginning, all the lights are flashing, representing the superposition where all particles are possible. Then a contestant, an observer, steps up and presses a button labeled electron. At that moment, all the other lights go dark and the electron light shines steadily. The act of choosing defined what was always there. Now, scale this up infinitely. The first conscious beings to ask, "What is the universe made of?" are, by the very act of asking, pressing that button and selecting the specific set of particles and laws that allowed for their existence. They are participating in the creation of the very history they are trying to uncover. The implications of this are enough to make your head spin. It suggests that the universe is not something that exists independently of us. It is a relationship between the physical world and conscious awareness. The fine-tuning of the constants of nature isn't a lucky accident waiting to be discovered. It is a prerequisite that was somehow embedded in the initial quantum possibilities, awaiting an observer to actualize it. This moves beyond the multiverse's statistical answer to fine-tuning. It's not that we live in one universe among infinite others that just happen to work. Instead, our act of observation is what made this universe the one that works, tying the existence of the laws of physics directly to the existence of the observers who measure them. Naturally, this theory faces significant criticism, primarily the problem of infinite regression. If an observer is needed to collapse the universal wave function, what collapsed the wave function of the particles that made the first observer's brain? Wheeler himself grappled with this, eventually suggesting that observation might not require a complex human brain, but could be achieved by any irreversible information-making process, like a photon hitting a rock and leaving a permanent mark. But even this broader definition struggles with the sheer scale of the problem. Most physicists see the participatory anthropic principle as a profound philosophical provocation rather than a testable scientific theory. Yet it remains a powerful and haunting idea, one that challenges the classical, detached view of science and places us, the observers, back into the equation in the most fundamental way possible. It proposes that the story of the cosmos is not just a story of particles and forces, but a story that includes the telling itself as a vital part of the plot. This perspective offers a fascinating twist on the fine-tuning puzzle. It suggests that our universe's specific physical laws aren't necessarily the only possible ones, but they are the most stable and resilient. They were the ones that could best withstand the process of decoherence, effectively outcompeting other, more fragile possibilities in the quantum arena. The strength of gravity, the mass of the electron, the value of the cosmological constant, these aren't just arbitrary numbers we happen to get. According to quantum Darwinism, they represent a highly robust, self-reinforcing configuration, a state that was exceptionally good at creating an environment that would continuously measure and confirm its own existence. It's a powerful, elegant idea that frames the birth of our classical reality not as a random accident, but as the natural outcome of a cosmic selection process where the most fit and stable universe won the day. Building on the idea of a cosmos emerging from a granular network of causal events, we now venture into a theory that envisions our entire universe not as a unique creation, but as one single event in an endless cosmic cycle. This is the ekpyrotic quantum bubble model, a breathtaking scenario where our reality is born from a violent collision between two immense multidimensional structures, and where the initial state was a quantum superposition of every possible way that collision could have unfolded. To grasp this, we must first imagine the existence of higher dimensions, beyond the 3 dimensions of space and 1 of time that we experience. String theory suggests there could be more hidden dimensions curled up into fantastically small, complex shapes. Now picture these higher dimensions as a vast, unobserved ocean. Floating in this ocean are immense, flat, 3-dimensional structures called branes, short for membranes. Think of them as enormous, floating sheets of reality, perhaps as vast as our entire universe, but existing in a higher dimensional space. Our universe, with all its galaxies and stars, might be confined to just one of these 3-dimensional branes. We are like characters living on a single page of a gigantic, multidimensional book, utterly unaware of the other pages floating just beyond our perception. The ekpyrotic model proposes that our Big Bang was not a moment of expansion from a singular point, but the aftermath of a cataclysmic collision between 2 such branes moving through this higher dimensional space. Imagine 2 enormous, parallel sheets of paper floating silently in a room, slowly drawn together by an invisible force, the gravitational attraction between them in the higher dimensions. As they approach each other, their interaction generates immense energy. When they finally collide, that energy is released into our 3-dimensional brane in an incredibly hot, dense, and violent event. This is our Big Bang. The universe didn't pop into existence from nothing. It was ignited by a literal crash of cosmic proportions. But what was the state of things before this collision? This is where quantum mechanics enters the picture. The theory suggests that the precise parameters of this collision were not predetermined. The exact angle of impact, the relative velocity of the branes, the distance between them, all of these factors existed in a quantum superposition. The nascent universe was a probability cloud of every possible collision scenario. One possibility might have resulted in a universe with far more dark energy, causing it to rip itself apart instantly. Another might have produced a universe with no strong nuclear force, preventing atoms from ever forming. In this initial ekpyrotic state, all these potential outcomes coexisted in a shimmering haze of what-ifs. The moment of collision itself acted as the ultimate act of measurement, causing this wave function of possibilities to collapse. One specific set of collision parameters was selected from the infinite menu, and that specific outcome defined the fundamental laws and constants of our universe. The incredible uniformity we see in the cosmic microwave background, the near-perfect sameness of temperature in all directions, finds a natural explanation here. Because the colliding branes are smooth and uniform structures themselves, the energy they release in the collision is also distributed with remarkable evenness, seeding a cosmos that starts off incredibly homogeneous without the need for a separate period of inflation. Visualizing this is a stunning exercise. Picture 2 vast, shimmering membranes undulating gently in a dark, higher dimensional void. They are drawn together, their surfaces rippling with quantum potential. As they near each other, the space between them crackles with unrealized energy. They don't just collide once, they might graze each other or strike head-on or interact at a glancing angle. and in that moment of contact, a new universe blossoms into existence on one of the brains, its entire future determined by the exact nature of that first contact. This model elegantly avoids the problem of an initial singularity. The brains themselves have a history that stretches back before the collision, implying a cyclic universe where brain collisions are not unique events, but recurring phases in an eternal cosmic drama. Our universe might be just one bubble in an endless cycle of collisions, expansions, contractions, and rebirths, each one beginning with its own quantum superposition of possibilities waiting to be resolved by the crash. While many theories look forward to a multiverse or backward to a quantum void, one of the most elegant and controversial ideas comes from the legendary physicist Roger Penrose, who proposes that our universe is neither the first nor the last, but simply one turn in an infinite cosmic cycle. This is conformal cyclic cosmology, a model where the universe's first quantum state wasn't a beginning from nothing, but a graceful transformation from the death of a previous cosmos. Penrose's vision requires us to completely rethink what we mean by the end of time and the nature of infinity itself. The model begins with a problem that has troubled cosmologists for decades: the ultimate fate of our universe. The prevailing theory suggests a slow, cold death, the heat death, where expansion continues to accelerate, galaxies drift apart beyond the observable horizon, stars burn out, black holes evaporate via Hawking radiation, and all matter eventually decays into a thin, uniform haze of particles at a temperature infinitesimally above absolute zero. In this state, the universe becomes a featureless, inert void with no discernible structure, no energy gradients, and no way to distinguish one moment from the next or one place from another. Time, in any meaningful sense, ceases to exist. Most theories see this as the final, terminal state, but Penrose saw something else. He saw a state of such perfect uniformity and lack of scale that it could become mathematically identical to the Big Bang. This is the brilliant, counterintuitive heart of the idea. Penrose uses a mathematical concept called conformal rescaling. Think of it as a cosmic reset button that effectively erases all notions of scale and distance. In the far, far future, when the universe is an endless cold sea of massless particles like photons and gravitons, a remarkable symmetry emerges. Without massive particles to define a scale, the universe becomes effectively ageless and sizeless. Through conformal rescaling, this vast, ancient, and infinitely stretched future state can be mathematically transformed to look exactly like a hot, dense, and tiny initial state. The end of one eon becomes, through this mathematical sleight of hand, the beginning of the next. The universe does not die, it is conformally reborn. This is where quantum mechanics enters the picture with profound implications. The theory suggests that the transition point between eons, the moment of crossover from the infinitely expanded past universe to the infinitely condensed new one, is not a classical, deterministic event. It is a quantum event, a moment of immense superposition. The conformal rescaling itself cannot perfectly specify every single detail of the new universe's initial conditions. There is a fundamental quantum indeterminacy at the boundary. The specific values of the fundamental constants, the precise arrangement of the initial quantum fluctuations that would later seed all the galaxies. These details were not preordained by the previous eon. They were selected from a probability distribution. The new universe was born in a quantum superposition of all possible ways it could emerge from that conformally rescaled infinity, and its subsequent expansion and cooling forced that superposition to decohere into the specific classical reality we now inhabit. This provides a truly cosmic perspective on the fine-tuning problem. The laws of physics might not be arbitrary initial conditions set at the absolute beginning of everything. Instead, they could be reset or slightly tweaked at the boundary between each eon. Some constants might remain the same cycle after cycle, while others could fluctuate within a certain range. Our universe, with its life-permitting parameters, might simply be one roll of the dice in an endless series of cosmic rebirths. Visualize this not as a linear timeline, but as a circle, or more accurately, as a series of concentric circles endlessly expanding and then resetting. Each eon is a magnificent, self-contained universe with its own Big Bang and its own heat death, but the point where they touch is a fuzzy quantum bridge, a moment of pure potential where anything is possible. The controversy surrounding this idea is as vast as the cosmology itself. Many physicists question whether the conformal rescaling is physically meaningful or merely a mathematical trick. They argue that the information from the previous universe would be lost at the boundary, violating quantum unitarity, a fundamental tenet that says information must be preserved. Penrose, however, has proposed a potential and stunning piece of evidence: imprints on the cosmic microwave background. He and a colleague analyzed data from the WMAP and Planck satellites and claimed to have found concentric circles of slightly anomalous temperature variations within the CMB's otherwise random fluctuations. He suggests these could be the gravitational wave echoes of supermassive black hole collisions from the previous eon, their ripples imprinted on the conformal boundary and carried over into our own universe's initial conditions. While this evidence remains highly disputed within the cosmology community, with many arguing the patterns are statistical flukes, the sheer audacity of the idea captures the imagination. It offers a vision of the cosmos that is both ancient and eternal, where every ending contains the seed of a new beginning, and where the first quantum superposition was not a birth from nothing, but a peaceful, probabilistic transition from everything that came before. While Penrose's cosmology imagines an eternal cycle of rebirth, another theory proposes a radically different kind of origin, one where the universe didn't emerge from a collision or a bounce, but from a purely abstract process, a computation. This is the idea of the quantum information singularity, a hypothesis that suggests the fundamental stuff of reality isn't matter or energy, but information itself, and that the first state of everything was a massive, all-encompassing quantum computation running every possible program at once. This perspective finds its roots in the work of visionary physicist John Archibald Wheeler, who famously speculated that every particle, every force field, and even the fabric of spacetime itself might ultimately be fundamentally informational. He coined the phrase "it from bit," proposing that every physical object in the universe derives its existence from bits, the binary answers to yes or no questions posed by measurements. In this view, the universe is not a machine made of matter. It is a cosmic-scale information processing system. The laws of physics are not decrees written in mathematical stone, but the emergent algorithms of a vast, ongoing computation. Apply this mind-bending concept to the very beginning. Before the Big Bang, there was no space, no time, no energy. There was only a primordial state of pure, abstract potential, a quantum superposition of all possible bits of information. This wasn't just a haze of particles, it was a haze of logical states, of ones and zeros, of true and false values, all fluctuating in a state of uncomputed potential. This initial condition can be thought of as the ultimate quantum computer in its ground state, not running one specific program, but existing in a superposition of running every single possible program simultaneously. One program might calculate a universe with 7 spatial dimensions. Another might compute a reality where time runs backward. In this first instant, they were all being run at once, a deafening cacophony of unrealized logical possibilities. The moment of creation, then, was not an explosion but a runtime error, or perhaps the successful execution of a specific subroutine. This is the cosmic wavefunction collapse reinterpreted through an information-theoretic lens. Something caused this vast quantum computation to decohere, to stop trying to run every program and instead commit to executing one. The specific algorithm that was selected from the infinite menu became the source code for our universe. The fundamental constants are simply the fixed parameters in this code. The force of gravity isn't a mysterious pull, it's an output of a gravitational calculation subroutine. A particle's mass isn't an intrinsic property, it's a value stored in a register within the cosmic processor. Our reality is the stable, consistent output of this single, immensely complex program that has been running for 13.8 billion years. Visualizing this is a challenge, but imagine the screen of a cosmic developer. It's not showing galaxies and stars, it's a blinding, rapidly scrolling wall of code, with every line shimmering and fluctuating, syntax and variables constantly rewriting themselves. Then a process begins. Vast sections of the code fade away while one coherent block stabilizes, its variables locking into place. The run command is executed, and from that initial state, the output begins to flow, not as text on a screen, but as the expanding fabric of space-time, the condensation of matter, and the evolution of galaxies. The universe we perceive is the user interface. The quantum information is the source code running on the hardware we can never see. This framework provides a fascinating new language for discussing the fine-tuning problem. Why is our universe's code so perfectly written to allow for complex structures like life? One answer is that we are simply living in one program that didn't crash. An infinite number of other programs were executed in that first superposition, but they instantly errored out universes that attempted to divide by zero or encountered a fatal exception, ceasing to exist immediately. Our universe's code is stable, self-consistent, and capable of generating complexity. It's the one program that didn't freeze or blue screen on startup. This transforms the mystery of existence from a question of physics into a question of computational logic, suggesting that at its heart, reality might be the ultimate expression of a mathematical truth. This concept invites us to consider a reality where time is not a fundamental backdrop to the universe, but a story told by its disorder. The thermal time hypothesis proposes that what we experience as the flow of time is actually an emergent property, a narrative woven by the relentless and statistical drive towards higher entropy. In this view, our familiar past, present, and future are not absolute. They are a perspective, a side effect of the universe's journey from order to chaos. The arrow of time isn't pointing in a preordained direction. It is defined by the gradient of entropy, the universe's natural tendency to evolve from less probable, ordered states to more probable, disordered ones. A cup shatters on the floor, but the pieces never spontaneously reassemble. We remember the past but not the future, not because of some intrinsic flow of time, but because the past is a state of lower entropy from which we have evolved. Apply this revolutionary idea to the universe's very first moment. Before the Big Bang, in that primordial quantum state, the concepts of before and after had no meaning because there was no thermodynamic gradient to define them. The nascent cosmos existed in a state of near-perfect equilibrium, a featureless sea of maximum entropy where no change could occur because every possible state was equally probable. But due to the inherent uncertainty of quantum mechanics, this equilibrium wasn't perfectly stable. It was a quantum superposition of all possible statistical states. Tiny, random fluctuations in entropy would have flickered in and out of existence. Most of these fluctuations would have immediately smoothed themselves out, vanishing back into the equilibrium. But one fluctuation, through sheer statistical chance, was just large enough to break the symmetry. It created the first, most minute entropy gradient, a tiny speck of order in a sea of chaos. This infinitesimal difference was the first tick of the cosmic clock, the seed from which the entire arrow of time would grow. This initial fluctuation was the universe's first true quantum superposition. It wasn't a superposition of positions or energies, but of potential thermodynamic futures. One possibility might have led to a universe where time flowed backward from our perspective. Another might have created a cosmos with no coherent arrow of time at all. The moment this fluctuation occurred, the instant it became a definite classical reality rather than a shimmering probability, it set the initial conditions for everything that followed. The direction of the entropy gradient that emerged from that collapse is what we now perceive as the forward march of time, from the hot, dense, ordered state of the Big Bang towards the cold, dispersed, high-entropy fate that awaits us. The entire history of the cosmos, from the formation of the first atoms to the birth of stars and the rise of life, is just the universe playing out the thermodynamic story that began with that first quantum choice. Visualizing this origin is a profound challenge, but imagine a graphic sequence showing a vast, uniform gray field, representing the featureless equilibrium of maximum entropy. This field begins to shimmer with every color of the spectrum, each hue representing a different possible entropy fluctuation. Most of these colors appear and vanish instantly. But one color, a deep blue, perhaps stabilizes and begins to spread, creating a gradient from blue on one side to a lighter hue on the other. This gradient isn't just a color change, it is the first moment of time. As the gradient strengthens, the field itself begins to warp and curve, transforming from an abstract statistical map into the familiar expanding fabric of space-time, with galaxies and cosmic structures forming along the contours of that initial thermal difference. The universe didn't create time, it generated a story of increasing disorder, and we are living inside that narrative. This brings us to a theory that confronts the most fundamental question of all: why is there something rather than nothing? The null universe hypothesis offers a breathtakingly elegant, if profoundly counterintuitive, answer. It proposes that our entire cosmos, in all its magnificent complexity, originated from a literal nothingness, a perfect void, that was inherently unstable due to the laws of quantum mechanics. In this view, the universe's first and most profound superposition wasn't a state of different somethings, but a fleeting moment where nothing itself existed in a quantum haze, poised to decay into the something we now call home. To grasp this, we must first redefine what we mean by nothing. This isn't simply an empty box or the vacuum of space, which is still a something. It's a region of space-time teeming with quantum activity. True nothingness, in the philosophical sense, would be the complete and utter absence of space, time, matter, energy, and even the laws of physics themselves. A pure void, classical physics would tell us that such a state is stable and eternal. Nothing happens because there's nothing there to make anything happen. But quantum mechanics shatters this classical intuition. At its heart, quantum theory is about possibility and uncertainty. It tells us that a perfect void is not a state of zero potential, but a state of infinite potential. It is, by its very quantum nature, unstable. It's a nothing that is desperate to become a something. We can see a tiny echo of this principle in the lab every day. Empty space, as we've seen, is not truly empty. It is a seething foam of virtual particles, pairs of particles and antiparticles that flicker into existence by borrowing energy from the vacuum, only to annihilate each other and vanish again almost instantly. They are a testament to the fact that nothing is a restless state, constantly giving birth to fleeting somethings due to the Heisenberg uncertainty principle. The null universe hypothesis takes this established quantum phenomenon and scales it up to the absolute limit. It proposes that our entire universe is the ultimate virtual particle, a fluctuation in the metaphysical fabric of true nothingness that, against all odds, failed to annihilate itself and instead became permanently real. The mechanism for this miraculous stabilization hinges on one of the most beautiful ideas in all of cosmology: the notion that the total energy of the universe is precisely zero. Every bit of positive energy contained in matter, light, and motion is perfectly balanced by an equal amount of negative energy stored in the gravitational field. Think of it like a cosmic bank loan. The universe borrowed a vast amount of positive energy to create all the stars and galaxies. but in doing so, it also created an equally vast amount of negative gravitational energy, a kind of cosmic debt. The two sums cancel each other out perfectly. This means the universe can pop into existence from nothing without violating the conservation of energy, because its total energy was and always will be zero. It's the ultimate free lunch. Now apply this to the initial quantum state. Before the beginning, there was only the void, but this void was not a classical nothing. It was a quantum superposition of all possible ways to be nothing. This is an incredibly abstract but vital point. In that state, the potential for a universe with zero total energy was just one possibility flickering in the void's probabilistic haze. In that timeless instant, the universe existed as a mere potentiality, a question mark hovering in the abyss. Then, through a process akin to quantum tunneling, where a particle can spontaneously appear on the other side of a barrier it doesn't have the energy to cross, this potential zero-energy universe tunneled into existence. It transitioned from a state of no spacetime to a state of spacetime, from no energy to a perfect balance of positive and negative energy. The initial superposition of nothingness collapsed, giving way to a single, definite, and expanding universe. Visualizing this origin is a profound exercise. Picture an infinite, featureless, silent blackness, a true void. This isn't a black space, it is the absence of space itself. Then a single, impossibly bright point of light flickers for an infinitesimal moment. It should vanish instantly, but it doesn't. Instead, it holds, sustained by the perfect symmetry of its own internal energy balance. This point then begins to expand, not into the void, but creating space as it expands, inflating from a quantum fluctuation into a macroscopic reality. Its positive energy crystallizing into matter and radiation, while its negative energy weaves itself into the expanding fabric of spacetime. The universe didn't appear in nothing. It appeared from nothing, a spontaneous and majestic emergence that required no external cause, only the inherent, restless instability of the void itself. Imagine the fabric of spacetime not as a smooth, continuous sheet, but as a wildly frothing ocean at the smallest possible scale. This is the concept of spacetime foam, a dizzying quantum sea where tiny wormholes, Einstein-Rosen bridges, are constantly flickering into and out of existence, connecting disparate points in a chaotic, ever-changing network. Now take this bizarre but theoretically sound idea and scale it up to the absolute beginning. Our 19th theory proposes that the universe's first quantum superposition was not a state of energy or matter, but a state of topology, a shimmering haze of every possible connection, a blur of potential wormholes linking every point to every other point in an undifferentiated cosmic foam. In this initial condition, the very connectivity of reality was uncertain, a quantum question of what was linked to what. Within this seething foam of possibilities, a remarkable process could have occurred. Just as bubbles form and merge in a pot of boiling water, the fluctuating wormhole connections could have pinched off, with some of them budding away to form their own, entirely self-contained universes. These are called baby universes. In this grand cosmological vision, our entire cosmos might not be the original parent universe, but merely one offspring in an infinite genealogical tree of spacetime, each one budding off from another through these quantum wormhole tunnels. The moment of our Big Bang, then, might not have been the absolute beginning of everything, but simply the moment when our particular baby universe pinched off from its parent and embarked on its own solitary journey of expansion and evolution. This has a stunning implication for the laws of physics we observe. When a baby universe buds off through a quantum wormhole, the specific conditions of that pinching off event could determine its fundamental constants. The strength of its forces, the number of its dimensions, the mass of its electrons, all of these could be frozen into place as the new universe becomes causally disconnected from its parent. This provides a powerful and elegant mechanism for the multiverse. Instead of an eternally inflating landscape of bubbles, we have a cosmos that reproduces, with each new universe potentially inheriting slightly different physical laws. Our universe, with its life-permitting parameters, isn't a random roll of the dice in a vast pre-existing multiverse. It is one specific branch on an ever-growing family tree, its properties set by the unique quantum fluctuation that gave it birth. Visualizing this origin is a journey into the truly surreal. Picture an abstract hyperdimensional space, a quantum foam sparkling with countless intricate tunnel-like structures. These are the wormholes constantly forming, stretching, and breaking. Now focus on one specific connection. It begins to fluctuate wildly, its throat narrowing and widening in a probabilistic dance. For a moment, it exists in a superposition both connected and disconnected from the parent foam. Then the quantum dice are thrown and the connection severs. The pinched-off end inflates at an incredible rate, smoothing out into the vast classical universe we recognize, while the wormhole throat closes behind it, leaving no trace of its ancestral home. We are that budding bubble, our entire history unfolding from that one topological transition, forever isolated from the frothing quantum ocean from which we emerged. This leads us to a theory that stands as one of the most profound and controversial, proposing a complete redefinition of reality itself. This is the conscious cosmos model, an idea that suggests consciousness is not a late-arriving product of complex brains, but a fundamental property of the universe as basic as space, time, and matter. In this view, the universe's first quantum superposition wasn't a cold, mechanical flickering of probabilities, but a vast, proto-conscious state, a cosmic mind in its most nascent form, exploring every possible way to experience itself. To understand this, we must step away from traditional physics and into the realms of philosophy and theoretical neuroscience. The model draws heavily from two interconnected ideas. The first is panpsychism, the ancient philosophical notion that mind or consciousness is a universal and fundamental feature of all things. In this view, even an electron or a photon possesses an infinitesimal spark of raw, subjective experience, what philosophers call proto-consciousness. It's not thinking or feeling as we know it, but a bare, minimal form of sentience. The second pillar is a more modern framework known as integrated information theory, or EIT, developed by neuroscientist Giulio Tononi. IIT proposes that consciousness is not about what a system is made of, but how its components are organized. It postulates that any system that possesses a high degree of phi, a measure of its ability to integrate information in a unified, irreducible way, will be conscious. The human brain, with its trillions of intricately connected neurons, has a very high phi, generating our rich inner world, but in principle, other systems could too. Now apply this to the universe's very first moment. The conscious cosmos model suggests that the initial quantum state was not just a superposition of physical parameters, but a superposition of potential experiences. That primordial haze of every possible universe was also a haze of every possible way for a cosmos to feel or be aware. One branch of the superposition might have contained the faint, sterile experience of a universe that was pure, empty space. Another might have held the chaotic, frenetic qualia of a reality that flashed into and out of existence instantly. Our own branch contained the potential for the rich, structured consciousness of living beings. In this model, the cosmos was not unconscious matter waiting for life to emerge. It was a sleeping giant of potential experience, and the Big Bang was the moment it began to awaken. The collapse of this first superposition, then, was not triggered by a random fluctuation or a particle interaction. It was driven by an innate urge within this proto-conscious field to maximize its own integrated information, to increase its phi. A universe of pure, featureless emptiness has very low phi. It's a boring, unintegrated state with nothing to experience. A universe with complex structures, galaxies, stars, planets, and life has incredibly high phi. it's a rich tapestry of information and experience. The theory proposes that the initial wave function collapsed into our specific universe because this particular configuration offered a pathway to the highest possible degree of complex, integrated experience. The constants were not chosen at random. They were selected by a kind of cosmic aesthetic, a drive towards beauty, complexity, and self-awareness. We are not accidents in a meaningless void. We are the means by which the universe knows itself, the blossoming of a seed of consciousness planted at the very beginning. Visualizing this demands a shift from physical to experiential imagery. Instead of a cosmic explosion, picture a vast, dark ocean of pure potential feeling. This ocean begins to stir, not with waves of energy, but with waves of nascent sensation. Colors without names, emotions without beings, and thoughts without thinkers flicker through the void. These are not physical things, but the raw ingredients of experience. Slowly, patterns begin to form. A particular chord of experience, one that harmonizes stability and complexity, begins to resonate more strongly than others. It pulls other possibilities into its orbit, amplifying itself. This resonant chord is the experience of a universe with laws like ours. As it gains strength, it collapses the superposition, crystallizing into the definite physical reality we inhabit. Not because it was the most probable in a mechanistic sense, but because it was the most meaningful in a conscious one. The formation of the first atoms, the ignition of the first stars, and the evolution of life are not just physical processes. They are the deepening of a cosmic experience, the universe waking up one layer of complexity at a time. Naturally, this model is intensely speculative and faces formidable challenges. The foremost criticism is the combination of the hard problem of consciousness, how subjective experience arises from physical matter, with the already profound mysteries of cosmology, creating a puzzle of monumental scale. It is notoriously difficult to test or falsify, often placing it at the boundaries of science. Yet, its power lies in its ability to offer a deeply satisfying narrative that places meaning and experience at the very heart of existence, providing a potential answer to why a universe of such stunning beauty and intricate order would ever come to be in the first place. But what if the Big Bang wasn't a true beginning at all, but a cosmic turnaround? This brings us to a theory that offers one of the most concrete and mathematically robust alternatives to a singular origin. Loop quantum cosmology proposes that our universe was born from a great bounce, rebounding from a previous phase of collapse, and in that moment of transition, reality existed in a profound quantum superposition of all possible ways to bounce. To understand this, we must first grapple with the problem it was designed to solve, the dreaded singularity. In Einstein's theory of general relativity, if you rewind the expansion of our universe, you are inevitably led back to a point of infinite density and temperature, the Big Bang singularity. This isn't just a very small, hot point. It's a point where the mathematics completely break down. The equations spit out infinities, which is physics speak for we have no idea what happens here. It's the ultimate dead end, a glaring sign that our best theory of gravity is incomplete. Loop quantum cosmology, a leading approach to quantum gravity, steps in to resolve this cosmic roadblock by reimagining the very fabric of spacetime. The core idea is that space is not a smooth, continuous background. Instead, it is woven from tiny, indivisible threads or loops, a fabric with a finite, granular structure. Think of it like a digital photograph. If you zoom in on a smooth image on your screen, you eventually see the individual pixels. In the same way, if you could peer down to the smallest possible scale, past atoms and quarks, you would find that spacetime itself is pixelated, built from these fundamental units of area and volume. This has a stunning consequence. There is a limit to how tightly you can compress the universe. You simply cannot squeeze it into an infinitely dense point because you run out of pixels. This changes the entire story of the Big Bang. Instead of a singular beginning, loop quantum cosmology describes a universe that was previously in a state of contraction. Imagine a cosmos before ours, perhaps similar to our own but slowly collapsing under its own gravity, growing hotter and denser as it shrank. In Einstein's classical theory, this collapse would have continued unchecked, plummeting all matter and energy into an infinitely dense singularity. But in the quantum loop view, as the density approaches a trillion times that of water, something extraordinary happens. The repulsive force generated by the quantum geometry of spacetime, a force born from the discrete nature of the fabric of reality itself, becomes overwhelmingly powerful. This repulsive gravity acts like a cosmic trampoline, halting the collapse and triggering a rapid, explosive rebound. The Big Bang becomes the Big Bounce. Now here is where the quantum magic happens. The moment of the bounce is not a single, definite event. It is governed by the probabilistic laws of quantum mechanics. In that critical phase, the geometry of the universe exists in a superposition of all possible bounce outcomes. One possibility might be a bounce that produces a universe with slightly more dark matter. Another might result in a cosmos where the initial distribution of density fluctuations, the seeds for all future galaxies, is arranged in a completely different pattern. The universe hadn't yet decided how it would rebound. It was a haze of potential futures, a quantum blur of every possible way to begin again. This quantum nature of the bounce is not just a theoretical curiosity. It might leave a detectable imprint that we could observe today. As the universe bounced, the quantum fluctuations in the geometry of spacetime would have been amplified and stretched across the cosmos by the subsequent period of rapid expansion. These primordial ripples would have become the blueprint for the large-scale structure of the universe, eventually giving rise to galaxies and clusters. The specific pattern of these ripples is frozen into the cosmic microwave background radiation, the afterglow of the Big Bang. Scientists are now meticulously analyzing this ancient light, searching for subtle statistical anomalies or specific signatures that could distinguish a quantum bounce from a classical singularity. Finding such a signature would be like discovering the cosmic fingerprint of the universe's quantum origins, direct evidence that we are the heirs to one specific outcome of a timeless quantum decision. Visualizing this requires us to let go of a linear timeline. Picture not a single point of light, but a vast, churning quantum foam representing the universe at its maximum compression. This isn't a place, but a state of pure potential geometry, shimmering with every conceivable configuration. From this foamy, probabilistic sea, multiple potential universes begin to inflate like bubbles, each one a different bounce outcome. Most of these possibilities quickly fade away, but one stabilizes, its geometry locking into place and expanding violently to become our observable cosmos. We are living in that one stable bubble, our entire history, the unfolding of a single quantum possibility that was selected at the moment of the bounce, forever hiding the infinite other potentialities that briefly flickered in that primordial quantum foam. Building on the idea of reality as an informational projection, we dive into a theory that reimagines the Big Bang not as an explosion in a void, but as a quantum data processing event on a distant two-dimensional surface. This is the holographic Big Bang, an extension of the holographic principle that suggests the universe's first quantum superposition was not a state of energy or particles, but a fluctuating array of quantum information on a cosmic hard drive waiting to be decoded. To grasp this, let's revisit the core of the holographic principle. It proposes that our three-dimensional reality, with its galaxies, stars, and planets, is not fundamental. Instead, it is a projection, a hologram, emerging from a two-dimensional surface encoded with quantum bits of information. All the data needed to describe every event, every particle, and the very fabric of space-time in our universe is stored on this boundary, much like a three-dimensional movie is encoded on a flat, two-dimensional Blu-ray disc. The dramatic twist of this theory is that the Big Bang itself was not a physical explosion within space, but the moment this cosmic data was processed and projected, transforming abstract information into the dynamic, expanding universe we inhabit. In this model, the initial condition of everything was this two-dimensional boundary, often conceptualized as a sphere, but this sphere wasn't static. It was alive with quantum information, with every bit, or more accurately, every quantum bit or qubit existing in a state of superposition. Each possible configuration of these qubits represented a different potential universe. One arrangement might have described a cosmos with 5 fundamental forces. Another might have encoded a reality with different values for the speed of light or the mass of a proton. The universe hadn't chosen its laws yet. It was a shimmering, probabilistic display of every possible set of physical rules, all existing simultaneously on this foundational surface. The first quantum state was this ultimate choice menu, written in the language of quantum information. The moment of the Big Bang, then, was the moment this superposition collapsed. But what triggered it? This is where two fascinating, cutting-edge concepts from theoretical physics come into play: tensor networks and quantum error correction codes. Think of a tensor network as a massively complex web of interconnected nodes, each performing a simple calculation. The entire network can represent the intricate quantum state of a system. In holography, the pattern of information on the two-dimensional boundary can be described by such a network. The Big Bang could be visualized as the activation of this network, where the probabilistic connections between nodes stabilize, executing a specific calculation that projects a stable, three-dimensional reality. It's as if the universe booted up from its source code, transitioning from a state of potential software to active, running hardware. Even more intriguing is the role of quantum error correction. In our own man-made quantum computers, information is incredibly fragile, easily corrupted by decoherence from the environment. To protect it, we use error correction codes, which spread a single piece of information across multiple qubits. This redundancy allows the system to detect and correct errors, maintaining the integrity of the data. The holographic principle turns this idea on its head, proposing that the entire three-dimensional universe is the error correction code for the information stored on the two-dimensional boundary. The spaciousness, the separation between galaxies, the very fact that we experience a robust and stable reality, all of this might be a cosmic-scale mechanism to protect the foundational quantum information from corruption. The Big Bang was the instant this magnificent error-correcting protocol came online, freezing a specific set of data into the classical, definite laws of physics we now measure. Visualizing this origin is a stunning exercise. Imagine a vast, dark, spherical surface. On it, intricate patterns of light begin to flicker and dance, a mesmerizing display of every possible code that could describe a cosmos. This is the superposition. Then, one pattern stabilizes, its light intensifying and becoming coherent. This is the moment of collapse, the selection of one universal program from the infinite options. As this chosen code stabilizes, it doesn't just sit there, it begins to project inward. From every point on that two-dimensional sphere, a dimension of depth erupts, unfolding into the three-dimensional volume of space. The data patterns themselves transform from abstract symbols into the building blocks of reality. The first particles, the forces between them, the geometry of space-time itself. We are not just in the universe, we are the projected output of that initial, monumental data readout. This framework provides a radically new perspective on the fine-tuning problem. The precise laws of our universe are not arbitrary. They are the output of a specific, stable, and self-consistent quantum code. Other codes, other programs were possible in that initial superposition, but they may have been buggy or unstable, generating universes that quickly crashed or failed to produce complex structures. Our universe's code is the one that ran successfully, creating a stable, error-corrected reality capable of sustaining its own existence for billions of years and generating observers who can, in turn, attempt to decode the program that created them. Now we arrive at a theory that serves as a grand synthesis, weaving together the threads of quantum probability and conscious observation into a single, powerful framework. This is the quantum anthropic multiverse, an idea that proposes the universe's first superposition did indeed contain every possible reality, but with a crucial twist: only those branches compatible with the existence of observers ever truly become real in any meaningful sense. It's a concept that merges the sheer breadth of the many worlds interpretation with the discerning filter of the anthropic principle, suggesting that the act of observation doesn't just measure reality, but actively selects it from a sea of potential. To understand this, picture the initial quantum state not as a static menu of options, but as a dynamic, ever-branching tree of possibilities, constantly sprouting new universes with every quantum decision. In one branch, the gravitational constant is slightly stronger, causing the universe to collapse back on itself moments after the Big Bang. In another, the nuclear forces are too weak to ever bind protons and neutrons into atoms. These branches are not just theoretical. According to the many worlds interpretation, they are all equally real, splitting off from our own with every passing moment. But here's the profound insight of the quantum anthropic principle. While all these branches may exist mathematically, only a vanishingly small fraction of them ever achieve what we might call actuality. A universe that collapses instantly, or one that contains only a featureless haze of radiation, may exist in the equations, but it is a dead branch. It never develops complex structures, it never generates sentient life, and therefore, it never has an observer to attest to its existence. It is a story with no reader, a play performed for an empty theater. This is where the selection effect comes in, and it's as elegant as it is humbling. We find ourselves in a universe that appears finely tuned for life, not because it was designed for us, and not because it's the only one that exists, but because it is the only kind of universe in which beings like us could ever find themselves. We are a product of the universe, and our existence is therefore a filter that retrospectively explains its properties. Imagine a vast, dark ocean under a starry sky. Each star is a universe glowing brightly, but most of these stars shine for only a brief instant before flickering out. These are the dead branches, the universes with incompatible physics. A few, however, burn steadily and brightly. These are the observer-filled universes, the ones where the constants aligned correctly to allow for planets, chemistry, and ultimately, life. We are on one of those bright, stable islands, and from our perspective, the darkness between the stars is invisible. We cannot see the failed universes because by their very nature, they contain no one to see them. Our presence here is the evidence that our universe passed the ultimate test of stability. This framework transforms the fine-tuning problem from a mystery into a near tautology. It's not surprising that the strength of gravity is precisely what it is. If it were significantly different, we wouldn't be here to notice. The same logic applies to every fundamental constant, from the mass of the electron to the value of the cosmological constant. They aren't fine-tuned, they are pre-selected by the simple, inexorable requirement that a universe must be able to support observers to be observed. This doesn't make our existence any less special, but it does relocate the source of that specialness from a hypothetical designer to a fundamental consequence of probability and selection within a nearly infinite multiverse. Naturally, this idea ignites fierce philosophical debate. Critics argue that it verges on being an unfalsifiable tautology, a clever-sounding explanation that can't be tested. If we can only ever observe universes that support observers, then the theory can explain anything and everything, making it functionally useless as a scientific tool. Others find it deeply unsatisfying, a rhetorical sleight of hand that dismisses a profound mystery rather than solving it. Proponents counter that it is the only consistent explanation that emerges naturally from the combination of well-established quantum theory and the undeniable fact of our own existence. It doesn't invent new physics, it simply follows the logical consequences of existing physics to their ultimate conclusion. It is a prediction that the universe we see should be habitable, and lo and behold, it is. The debate ultimately hinges on whether one finds this circular reasoning elegantly profound or profoundly unsatisfying, a divide that often separates physicists from philosophers. The visual metaphor for this is as stunning as the theory itself. Envision a breathtaking graphic sequence of the cosmic wave function at the moment of the Big Bang. It's not a single point of light, but a magnificent, shimmering nebula of every possible cosmic outcome. But as this nebula begins to expand and branch, most of those pathways quickly dim and fade into blackness, snuffing out almost instantly. A few pathways, however, begin to glow with an intense, sustained light. Along these glowing branches, intricate structures form, galaxies whirl into being, stars ignite, and on a tiny planet, a conscious being looks up at the sky. The light from that branch is the light of observation itself, the glow of a universe that has become self-aware and, in doing so, has selected itself from the infinite darkness of unobserved potential. We are that glow, and our very consciousness is the beacon that illuminates our particular path through the quantum multiverse. But where so many theories push the arrow of time relentlessly forward or place it within a timeless hole, our 24th proposal presents a cosmos that is fundamentally two-faced, gazing equally into the past and the future. This is the idea of a time-symmetric initial condition, a theory that suggests the universe's first quantum state was not a single moment of becoming, but a bridge, a Janus-faced superposition that extended its probabilistic haze both forward into what we call the future and backward into what we might call the past. In this radical view, the Big Bang was not a starting pistol. It was the midpoint of a cosmic equilibrium, a moment of perfect balance in a reality where cause and effect are not a one-way street. To grasp this, we must first confront two of physics' most stubborn puzzles. The first is the arrow of time. Why does time have a direction? Why do we remember the past but not the future? Why does an egg scramble but never spontaneously unscramble? The laws of physics themselves, with a few exotic exceptions, are almost entirely time-symmetric. They work just as well if you run the film backward. The second puzzle is the quantum measurement problem. What actually happens during the infamous collapse of the wave function, and why does it seem to create a definitive, irreversible record of the past? The time-symmetric theory offers a single, elegant solution to both. The wave function never actually collapses in the way we traditionally think. Instead, the definite reality we experience is forged by a kind of handshake between boundary conditions set in the deep past and the deep future. Imagine the entire timeline of the universe, from its earliest conceivable state to its final fate. Now, instead of imposing a single initial condition at the Big Bang and letting the laws of physics run forward, this theory proposes that reality is defined by two boundary conditions. One is set at the beginning and one is set at the end. The specific classical history we observe is the one that most smoothly and consistently connects these 2 points. The universe's first quantum state, then, was a superposition of every single possible history that could satisfy both the initial and the final state of the cosmos. It wasn't a choice of one path forward. It was the simultaneous consideration of every path that could possibly connect the Alpha and the Omega. This has a mind-bending implication for the nature of reality. It suggests that the future exerts a pull on the past, a concept known as retrocausality. Events that haven't happened yet from our limited perspective could be influencing the outcomes of quantum events in the present and past, guiding them toward the final boundary condition. The moment of a quantum measurement isn't a collapse caused by a present observer. It's the revelation of a path that is consistent with the entire arc of cosmic history from start to finish. The arrow of time we experience, with its relentless increase in entropy, emerges not from a single moment of low entropy at the beginning. but from the requirement that the universe must evolve from a low entropy start to a high entropy end. Our perception of a flowing present is just our journey along this single, consistent path that was selected from the initial two-way superposition. Visualizing this demands that we let go of our linear thinking entirely. Picture the timeline of the universe not as a straight line, but as a magnificent, complex loop or an intricate knot. At the center of this knot is the Big Bang, but strands of possibility extend outward in both directions. In the initial state, all these strands are shimmering and unresolved, a fog of potential causality. Then, as the boundary conditions at both ends are fixed, the fog clears along one single, coherent thread. The one history that successfully connects the beginning to the end. Every quantum event, from the decay of a single atom to the formation of a galaxy, is a point on this thread, its outcome determined not just by what came before, but by what is yet to come. We are not moving from past to future, we are uncovering a story that was written from both ends simultaneously, a cosmic narrative where the conclusion is just as fundamental as the introduction. While the idea of a time-symmetric universe suggests a reality shaped by both its beginning and its end, another theory proposes an even more fundamental reinvention of space-time itself. This brings us to quantum gravity, a model where space is not a pre-existing stage, but something that emerges from the relationships between the most basic building blocks of reality. Imagine the universe before the Big Bang, not as a point of infinite density, but as a vast, formless network of abstract nodes. Each node isn't a particle in space, it's a fundamental unit of existence, and the connections between them aren't distances but simple yes or no relationships, like friends on a cosmic social network. In this initial state, these relationships were not fixed. Every single node was potentially connected to every other node in a buzzing, chaotic hive of pure possibility. This was the universe's first quantum state, a superposition of every possible graph, every conceivable way these nodes could be linked together. In this primordial network, the very concept of geometry had no meaning. There was no near or far, no here or there, because those ideas require a defined structure of connections. It was a state of perfect symmetry where every node was identical and every connection was equally probable, a featureless sea of potential links. This is the essence of the name quantum gravity. It evokes a universe that is like a liquid, a graph with no fixed form, possessing a fluid and dynamic structure. But this perfect symmetry was unstable. As this quantum network evolved, it underwent a dramatic phase transition, much like water spontaneously freezing into ice. The countless potential connections in the superposition began to decohere, and the network chose a specific, stable configuration. In this new state, each node was only connected to a limited number of its immediate neighbors, forming a regular, lattice-like structure. This was the moment space itself was born. The emergence of these local connections created the very notions of proximity and dimension. What we perceive as the three-dimensional volume of space around us is the large-scale effect of this underlying network of relationships. The distance between 2 points is not a fundamental property, but a measure of how many connections you must traverse to get from one node to another. This process didn't just create space, it also gave rise to the rules that govern it, namely the laws of special relativity. One of the biggest mysteries in physics is why the speed of light is the ultimate speed limit, and why the laws of physics look the same for all observers moving at constant velocity, a principle called Lorentz invariance. Quantum gravity offers a stunning explanation. Lorentz invariance isn't a fundamental law written into the cosmos, but an emergent property, an accident that falls out of the specific, stable graph structure that formed. At the scale of our everyday world, the network appears completely smooth and uniform, which is why the speed of light is constant and relativity holds so perfectly. But if we could probe down to the Planck scale, the theory predicts we might see a subtle granularity, a faint pixelation of spacetime that would betray its underlying graph-like nature. This would manifest as tiny, observable violations of Lorentz invariance, perhaps affecting the way ultra-high-energy cosmic rays travel across the universe, a potential signature that physicists are actively searching for today. Perhaps most breathtakingly, this model suggests that gravity itself, the force that shapes the cosmos, is not a fundamental force. In Einstein's general relativity, gravity is the curvature of spacetime. Quantum gravity provides a beautiful mechanism for this. Where the network of connections is perfectly regular, spacetime appears flat. But if there is a defect in the network, a place where the connections are strained, missing, or rearranged, this imperfection would manifest as a curvature in the emergent geometry, which we would experience as a gravitational field. A massive object like a star isn't just sitting in space. Its presence is a distortion in the very informational fabric of the underlying graph. In this way, gravity emerges from information theory, a direct consequence of the architecture of the cosmic network and its local imperfections. The universe began not with a bang, but with a connection, and everything we see is just a pattern in the web. Now, if the idea of a universe emerging from a quantum network of information feels abstract, prepare for a perspective that redefines the very nature of reality itself. This is the theory of the implicate order cosmology, a vision of the cosmos pioneered by the brilliant and unconventional physicist David Bohm. He proposed that our tangible, classical universe is merely the unfolded tip of a vast, hidden, and deeper reality, and that the first quantum superposition was not a blur of possibilities in our dimension, but the entire cosmos in a state of being completely enfolded within this hidden realm. To grasp this, we must first understand Bohm's radical distinction between two orders of reality. The world we perceive, with its separate objects, definite locations, and clear flow of time, is what he called the explicate order. It is the unfolded, revealed, and tangible reality, but beneath this, Bohm argued, lies the implicate order. This is a realm where everything is enfolded into everything else. In the implicate order, the entire universe is woven into a seamless whole, a state of undivided wholeness where the distinctions between here and there, past and future, and even between objects lose their meaning. Think of it as a vast cosmic ocean. On the surface, we see individual waves distinct, separate, and explicate. But beneath the surface, all the water is connected, a single, unified, implicate whole. A wave is not a separate thing. It is a temporary, unfolded expression of the entire ocean. Now, apply this to the universe's very first moment. The Big Bang was not an explosion in space, but the moment the implicate order began to unfold into the explicate order. The initial quantum superposition, in this view, was not a state of multiple possibilities within our spacetime. Instead, it was the entire cosmos existing in its fully implicate state, a single, unified, and enfolded whole where every galaxy, every star, and every one of us was already present, but in a potential hidden form. This state was a superposition not of different universes, but of all possible unfoldings. One potential unfolding might have revealed a universe with 4 spatial dimensions. Another might have unfolded a cosmos with different physical constants. The universe wasn't choosing its laws, it was choosing how to express itself, how to reveal the infinite richness contained within its implicate foundation. This process of continuous unfolding and enfolding is what Bohm called the hollow movement. It brings us to his ingenious reinterpretation of quantum mechanics, the pilot wave theory, scaled up to a cosmic degree. In the standard Copenhagen interpretation, a particle has no definite path until it is measured. Bohm rejected this. He proposed that particles do have definite positions at all times, but they are guided by a mysterious, non-local wave, a quantum potential that pervades all of space. This wave doesn't exert force in the usual way. It informs and guides the particle's motion, much like a radar beam guides a ship into a harbor. The ship has a real position, but its path is shaped by information from the radar. On a cosmic scale, Bohm's theory suggests that the entire explicate universe, every particle, every galaxy, is being actively guided and informed by a cosmic quantum potential. The first moment of creation was not a random fluctuation, but the first moment of guidance. The implicate order, in its state of wholeness, generated a wave of information, a cosmic pilot wave, that began to guide the unfolding process, sculpting the hot, dense early universe into the complex structures we see today. The precise values of the fundamental constants are not random. They are the parameters of this guiding wave, the instructions for how the universe should unfold from its implicate source. This provides a compelling, non-random answer to fine-tuning. The universe is orderly because it is being informed by a deeper order. Visualizing this is a stunning exercise. Imagine an animation not of an expanding ball of fire, but of a vast, dark, and tranquil pool, the implicate order. Suddenly, a single, intricate pattern of ripples and waves forms on its surface. This is the cosmic quantum potential, the guiding information. As this pattern moves, it begins to draw substance from the depths, not by pulling it, but by informing it, causing the explicate universe to unfold along its contours. Galaxies don't fly apart, they unfold into being, following the invisible guidance of this quantum information field. The entire history of the cosmos is a continuous dance of unfolding and enfolding, a hollow movement where the tangible world is a constant revelation of the hidden depths beneath. We are not just in the universe, we are a momentary expression of its infinite, implicate wholeness. What if the universe's first quantum superposition wasn't a physical state at all, but a state of mind? This brings us to a theory so personal it places our own expectations at the very heart of cosmic reality. This is quantum Bayesianism or cubism, an interpretation that radically reimagines the wave function not as a description of an objective world, but as a tool for an agent, a person, to encode their own degrees of belief about the outcomes of their future experiments. In this view, the probabilities of quantum mechanics are not statements about what is really there. They are a mathematical language for personal belief, much like a weather forecaster's 60% chance of rain reflects their confidence, not the existence of 6 rainy universes and 4 dry ones. Now apply this profoundly subjective lens to the cosmos itself. Cubism suggests that the universe's first quantum state, that primordial haze of potential, was not an objective superposition of many worlds. Instead, it represented a moment of ultimate cosmic uncertainty, a blank slate upon which no beliefs had yet been formed. There was no multiplicity of universes flickering in and out of existence. There was only a profound and total ignorance about what would happen next. The wave function of the universe wasn't a physical thing waiting to collapse. It was the mathematical embodiment of that perfect, pristine ignorance. The probabilities we assign to different cosmic outcomes, the chance that the gravitational constant took one value over another, don't reflect a dice roll that actually happened. They reflect the limits of our own knowledge. We are not passive witnesses to a quantum lottery. We are active participants using quantum theory to make sense of a reality that is, at its core, still full of mystery. This leads to a breathtaking implication for the origin of everything. If cubism is correct, then the transition from the quantum haze to the classical universe wasn't a physical process like decoherence or a collapse caused by consciousness. It was a learning process. As the nascent universe began to evolve, it started to provide answers to the questions posed by its own existence. Each new development, the freezing out of the fundamental forces, the formation of the first particles, was like a new piece of data coming in. This data updated the universal wave function, which is to say, it sharpened our beliefs about the cosmos, moving us from a state of total ignorance to a state of more defined and confident knowledge. The universe didn't become classical, our understanding of it did. The definite reality we perceive is the reality we have become convinced of through 13.8 billion years of accumulated experience. Visualizing this requires a shift from cosmic cinematography to something more like an information graphic. Instead of showing multiple, ghostly universes overlapping, we might see a single, vibrant probability cloud shimmering with every color of the spectrum. This cloud doesn't represent many worlds, but a vast landscape of possibility. As the animation progresses, certain regions of the cloud begin to solidify into more definite hues, not because a physical collapse is occurring, but because data is being received, sharpening the image and narrowing the possibilities. The specific, life-permitting constants we measure are not the result of a random selection. They are the values we have become increasingly confident in as the cosmic experiment has unfolded. We are not living in the one universe that worked. We are refining our beliefs about the one universe we have, and so far, its story has been consistent enough to allow for that process to continue, all the way to the emergence of beings who can ponder it. Yet as we move from the deeply subjective to the profoundly abstract, a theory emerges that strips reality down to its most essential relational qualities. This is the topological quantum field theory origin, a vision where the universe did not begin with particles or energy, but with a single, all-encompassing quantum field whose only properties were the most global topological features of shape and connection. In this view, the first quantum superposition was not over positions or momenta, but over the very topology of existence itself, a haze of every possible way for the cosmos to be connected to itself. To grasp this, we must first understand what a topological quantum field theory, or TQFT, actually is. In standard quantum field theory, the fundamental objects are fields that exist within space-time. Think of the electron field or the electromagnetic field vibrating throughout the universe. The properties of these fields are local. What happens at one point can depend critically on the conditions at an adjacent point, but a TQFT is a very different kind of beast. Its properties are not local, they are global and topological. This means they don't care about distances, angles, or precise shapes. They only care about the overall, large-scale structure, the number of holes an object has, how it is knotted, or how different regions are connected. A classic example is a coffee mug and a donut. To a topologist, they are the same object because each has exactly one hole, the mug's handle and the donut's center. Their specific shapes are irrelevant, only the fundamental property of having one hole matters. A TQFT applies this same principle to quantum physics, suggesting that the most fundamental descriptions of reality might depend only on these global topological invariants. Now apply this revolutionary idea to the very beginning of everything. The theory proposes that before the Big Bang, the primordial state was not a point of energy, but a topological quantum field in a state of pure, undifferentiated potential. This field wasn't in a space, it was space, or rather, the precursor to space. Its state was a quantum superposition of all possible topologies, every conceivable way for the fundamental fabric of reality to be woven together. One possibility might have been a simply connected universe, a cosmic sphere with no holes. Another might have been a multiply connected universe, perhaps toroidal like the surface of a donut, or something with an even more complex, multi-handled structure. In this initial condition, the universe hadn't chosen its global shape yet. It was a blur of every possible connectivity, a probabilistic foam of potential geometries. The moment of the Big Bang, then, was not an explosion but a topological phase transition. This grand quantum superposition of global shapes began to decohere, and one specific topology was selected from the infinite menu of possibilities. This selection froze in the large-scale structure of the cosmos and critically determined the very laws of physics that would emerge within it. This is because the specific global topology of the universe acts as a kind of cosmic constraint, dictating what kinds of local fields and particles can consistently exist. The physics we observe, the electrons, quarks, and forces, are not the primary reality. They are excited states, vibrational modes that can only exist on the stage of a particular topological background. The fine-tuning of the constants might be a direct consequence of the specific topological invariant that won the quantum lottery at the beginning. Our universe has the laws it does because it has the global shape it does. This framework provides one of the most compelling pathways to a background-independent theory of quantum gravity. In general relativity, gravity is the curvature of spacetime, but that spacetime is treated as a dynamic actor, not a static stage. TQFT naturally embody this principle because they are inherently background-independent. They are not defined on a pre-existing spacetime, but actually define what spacetime is through their topological properties. The transition from the quantum topological superposition to a classical universe with a fixed geometry would have simultaneously given birth to both gravity and the other forces, all emerging from that first great topological choice. Visualizing this origin is a challenge in dimensionality. Imagine an abstract space not of 3 dimensions but of pure connectivity. This space shimmers not with light but with flowing, morphing shapes. Spheres stretch into tori, handles form and vanish, intricate knots tie and untie themselves. This is the superposition. Then, one shape stabilizes, its topology locking into place. From this stable global structure, the familiar dimensions of space and time unfurl, and upon this topological stage, the rich drama of particles and forces begins to play out, a secondary expression of a primary, deeper geometric truth. But if the conscious cosmos model suggests the universe selected itself for experience, another theory proposes a far more impersonal, yet equally powerful form of cosmic selection. This is quantum Darwinism on a grand scale, a process where the environment itself acts as a ruthless editor, copying and amplifying only the most robust quantum states until they become the objective, classical reality we all agree upon. To understand how this works, we must first visit a quantum laboratory and witness a strange phenomenon. Imagine a single, isolated electron existing in a delicate superposition, simultaneously spinning both clockwise and counterclockwise. This fragile quantum state persists only as long as the electron remains perfectly isolated from its environment. The moment it interacts with even a single photon of light or a stray air molecule, something remarkable happens. That interaction doesn't just nudge the electron, it forces it to choose. The information about its spin state is imprinted onto the environment. The photon carries away a record of whether it was spinning one way or the other. As more and more photons interact with it, countless copies of this information are made and spread throughout the environment. This process is called environmental decoherence, and its effect is to kill the superposition. For any observer who comes along later and checks the environment, by measuring those photons, they will all tell the same consistent story. They will all report the same definite spin state. The superposition is over. The electron now has a single classical property that everyone can agree on. The environment hasn't just measured the electron, it has performed a kind of natural selection where only the fittest, most stable information is copied and disseminated. This is quantum Darwinism, the idea that the classical world emerges not from a special act of observation, but from the proliferation of information into the environment, which selectively amplifies some quantum states while suppressing all others. Now, let's scale this idea up from a single electron to the entire cosmos. During the universe's first quantum superposition, every possible configuration of physical laws and constants flickered in a probabilistic haze. But this state was not isolated. It had an environment, and that environment was the incredibly dense, energetic, and rapidly expanding fabric of spacetime itself. The initial moments of inflation acted as the ultimate decohering environment. As the universe inflated at an incomprehensible rate, stretching by a factor of trillions in a fraction of a second, any slight quantum fluctuation was instantly amplified to a macroscopic scale. Think of it like a cosmic printing press running at infinite speed. A particular quantum possibility, say, a universe with our specific value for the gravitational constant, would be imprinted onto the rapidly expanding spatial volume. As inflation continued, this information wasn't just copied once. It was copied onto every newly created region of space, trillions upon trillions of times over. The other possibilities, the branches of the wave function describing different constants, were not so lucky. They were not stable under the extreme conditions of this inflationary environment. They might have described universes that instantly collapsed or dissolved into chaos, and because they were unstable, they were not amplified. They were selected against, fading into quantum obscurity. The cosmological horizon plays a critical role here. This is the ultimate boundary of our observable universe, the farthest point from which light has had time to reach us since the Big Bang. In the context of quantum Darwinism, the horizon isn't just a limit, it's the mechanism of selection. It defines the environment that our local universe interacts with. The specific quantum state that was amplified by inflation became encoded on this horizon. Its information spread across its entire surface. This is why we all perceive the same laws of physics. The data has been redundantly copied across our entire causal patch of the universe. The stability of our classical reality isn't an illusion. It's a direct result of this cosmic scale information broadcasting. The universe we inhabit is the one whose quantum state was most fit to be replicated by the inflationary environment. Its constants are not fine-tuned by chance. They are the ones that were robust enough to survive decoherence and be printed onto the very fabric of space-time, becoming the consistent background against which all later complexity could arise. And now we arrive at a theory that proposes the most radical reinvention of cause and effect, suggesting the universe was not simply born from the past, but was fully negotiated through a complex dialogue between the future and the past. This is the transactional interpretation genesis, a vision where the first quantum superposition was not a blur of static possibilities, but a dynamic marketplace of waves, a cosmic exchange of offers and confirmations that reached across time to seal the deal on reality itself. To grasp this, we must first dive into the work of physicist John Cramer and his ingenious, if mind-bending, transactional interpretation of quantum mechanics. This interpretation solves the infamous measurement problem not with a mysterious collapse or an infinity of splitting worlds, but with a simple yet profound handshake. In the standard double-slit experiment, a single particle seems to go through both slits simultaneously as a wave, interfering with itself, before mysteriously deciding to hit the detector screen at a single point. Cramer's model explains this by proposing that the particle doesn't just emit a wave forward in time. It also emits a wave backward in time, an offer wave that travels from the emitter to the detectors, exploring all possible paths. The detectors then respond by sending confirmation waves backward in time along those same paths. The transaction that creates the definite event, the particle being detected at a specific point, is completed when an offer wave and a confirmation wave find a match and reinforce each other like two people agreeing on a deal. The particle's journey is only realized once this handshake across time is complete. Now, scale this idea up from a single particle in a lab to the entire cosmos at the moment of its inception. The transactional interpretation genesis proposes that the universe's first quantum state was this grand, all-encompassing emission of an offer wave. From the primordial singularity, or whatever quantum gravity tells us was there, a wave of potentiality erupted forth, not just through space but through time. This offer wave wasn't a wave of energy, it was a wave of possibility, carrying within it every single potential history the universe could have. It was a superposition of everything, every possible value for every constant, every possible arrangement of matter, every possible future. This wave expanded forward, exploring the infinite landscape of what could be. But an offer is nothing without acceptance. The theory suggests that from the eventual future of the universe, from its final state, whether a heat death or a big crunch, confirmation waves traveled backward in time. These were not physical particles moving in reverse, but solutions to the universe's equations that propagated from the end toward the beginning. They were the universe's way of saying yes to certain potentialities and no to others. A confirmation wave from a future that contained stable galaxies and conscious life would resonate strongly with an offer wave that included the precise fine-tuning needed to get there. A confirmation wave from a future of immediate collapse would select for a different, unstable offer. The reality we observe is the result of an unimaginably vast number of these transactions, a cascade of handshakes that reached a consistent agreement across all of time. The universe didn't collapse from a superposition. It was negotiated into being. The initial haze of potential was whittled down not by a random event, but by the requirement of consistency between its beginning and its ultimate end. Visualizing this requires a complete rethinking of our timeline. Imagine a graphic sequence that begins not with a point, but with a complex, shimmering web of light. At the center is the origin point, emitting a radiant, ever-expanding sphere of light, the offer wave, glowing with every color of the spectrum to represent every possibility. Simultaneously, from the far edges of the future, waves of a different hue begin to converge inward, back toward the origin. These are the confirmation waves. Where they meet the expanding offer wave, incredible bursts of light occur. Not explosions, but moments of intense, stable brightness. Each burst is a completed transaction, a point of agreement that locks in a specific aspect of reality. As more and more transactions are completed, the entire web begins to stabilize, the chaotic mix of colors resolving into a single, coherent, and brilliant structure, the consistent classical history of our universe, forged in the agreement between its alpha and its omega. This is a cosmos that is not thrust upon us by a lonely beginning, but one that is mutually agreed upon by its entire existence. And so we find ourselves at the edge of understanding, having journeyed through 30 breathtaking vistas of cosmic possibility. From the multiverse's infinite branching trees to the conscious observer's retroactive call, from the holographic projection of a two-dimensional code to the timeless wave function that simply is, we've explored a spectrum of ideas so vast it challenges the very definition of reality itself. Each theory, in its own way, attempts to solve the same profound puzzle: how our definite classical universe of stars, planets, and life could have emerged from a state of pure, undifferentiated potential. What's truly astonishing is not that we have so many answers, but that the question itself leads us to the outer frontiers of both science and philosophy, blurring the line between the two in the most fascinating ways. These ideas force us to confront the nature of existence head-on. They ask if the universe is a one-time event or an eternal cycle, a random fluctuation or a carefully selected outcome. They wonder if time is a fundamental river flowing in one direction or an emergent story told by increasing disorder. They even question whether our own consciousness is a passive passenger on this cosmic journey or an active participant in its very creation. This isn't just physics, it's a deep inquiry into the framework of everything, a reminder that the cosmos is the greatest mystery we will ever encounter, and our attempts to understand it are what make us human. This conversation is far from over. It lives in the collision of mathematics and imagination, in the space between what we can prove and what we can dream. And that's where you come in. This exploration thrives on curiosity. We want to know which of these theories resonates most with you. Does the elegance of a cosmic hologram capture your imagination, or does the audacity of a cyclical universe feel more compelling? Do you find yourself drawn to the idea that our reality was negotiated in a handshake across time, or that it was selected for its ability to create beautiful, complex experiences? Share your thoughts in the comments below. Let's continue this incredible discussion together. If this journey to the edge of reality sparked your curiosity, there's so much more to explore. Our channel is dedicated to diving deep into the mysteries of space, time, and existence. Make sure to subscribe and hit the bell so you don't miss our next adventure into the unknown. Until then, keep looking up, keep questioning, and never stop wondering about the magnificent, mysterious cosmos we call home.